Hi, and welcome to this session on the lab for Physics 4C. Today is March 22nd. Today's lab is on thermal expansion. It is really a short lab. It's probably the shortest lab that you're going to have in this class. And I'm going to go quickly through it. Again, I want you guys to remember to go through the rubric and see how labs are graded, and it's no different than the other labs. So I'm hoping that you guys will make sure you follow the rubric when you're filling out the lab. All of the labs usually have one. If not, now you know exactly how labs basically will be graded, in a sense that you have the name, the objective, the questions, the tables if there are any, and there are in this case, there are tables, graphs if there are any, and then conclusions and things of this nature and how they are graded. So without further explanations on this, that I'm hoping that you guys would have had a chance to go through it. This lab is on thermal expansion. This is part of chapter 17. I have something else going on the laptop. That's why I'm refreshing the laptop to make sure that it's actually uploading a class from before. Anyway, so let me share with you the screen. So basically what you're looking at in here should be the LAB05 thermal expansion. Again, your name, or the name of your name and the names of the people if you worked with more than if you worked with somebody else. This is in a nutshell the theory, okay, for it. If the temperature increases, the length of the material increases. This is to somewhat extent related to the elasticity of the material. And this is similar to that, basically. Delta L over L naught is how the percentage of growth of the element in the case of the linear expansion. This is what we're going to be exploring in here. Delta T in this case is a change in temperature, okay? So for some materials in here is the coefficient alpha. This is the coefficient of linear expansion. Remember, the volume expansion is related to the linear expansion by that number 3 times alpha is equal to beta, okay? For the volume expansion, it's the same thing. Delta V is equal to beta times V naught times the change in volume. So basically you heat up a material and it's going to change in all the directions, not necessarily in the line. So this is something that we talked about in the theory. So again, in class, so this is the alpha for some materials. For a particular case, for example, that interests us usually is the case of steel and also concrete, because if you build a building, you would want to know how much they change. The coefficients are not too far from one another. That's why actually steel is a good material to be used basically in construction, because the coefficients, they will expand in the same fashion, more or less. If you put, for example, aluminum 2.34 or lead 2.9, then in this case it has a higher coefficient of expansion, so it's going to protrude from the basically it's going to push against the concrete, and that is not good. Okay, you don't want that. You don't want any deformities coming from the material. So there are some engineering stuff in here related to construction and things like that, and building things, materials and things of this nature, okay? So anyway, this is basically what we showed in class 2. If you are not sure about this one, please let me know. The question 1 basically is saying for a solid, we define the volume expansion similar to the linear expansion as being V equal to V naught times beta times delta T, where beta is the coefficient of thermal expansion. Show that this coefficient is 3 times the linear expansion. And that is really boils down to the definition of the volume. You guys remember, the volume is just the length times length times length, length times width times height, okay? If it is a normal, if it's a sphere, it's the radius cubed, okay? When we use the Taylor expansion, let me quickly talk about that, because sometimes this becomes a question. If you did not really do this stuff in here before, like, you know, I don't know, right? Okay, let me share with you the screen. Let me stop sharing that screen and share with you the other screen, which is, no, not, I want just to share this note in here. Okay, so let's talk about that point for a moment, okay? Doesn't matter which shape you have, it's cubical shape, whatever, length times width times height. So this would be the volume in this case. If it's a sphere, for example, it's going to be, what is it? 4/3 of pi r cubed, okay? In either case, the volume in this case will change by the following. So from V to plus delta V, when the temperature changes, to alpha, L naught. So this is an old volume before the temperature has changed, okay? So this is, the new volume now is going to be the old volume plus delta V, the change in volume. So the new volume V is simply V naught plus delta V due to thermal temperature. So T went from T to T plus delta T. If that's the case and the volume at T is this much, so the new volume will be the new value that changes in here. So it's alpha times delta T times W naught, the width of the object, plus delta times L naught, I'm sorry, alpha times W naught times delta T, times again the height, which is H naught plus alpha times H naught times delta T, okay? If I do expand these terms in here, I will have L naught times W naught times H naught, which is the old volume V naught, plus the first term in alpha will have alpha times L naught times delta T times W naught times H naught. So it will have alpha times L naught, W naught, H naught is V naught, okay, times delta T, plus, it's the same term in here, W naught alpha delta T times L naught times H naught. So again, it will have alpha times W naught times L naught times V naught. That is actually, W naught times L naught times H naught, that is actually V naught. So again, alpha, I took alpha out, I'm sorry. So it's going to be V naught times delta T, plus another term in here that involves alpha also. Alpha H naught delta T times W naught times L naught. That too is another alpha times those stuff. Alpha, which I took it out, and it would be left with an H naught times W naught times L naught, and that is the old volume V naught times delta T, plus some linear terms, some quadratic terms in alpha squared terms. I'm going to ignore anything of the order of alpha squared. That is the whole purpose of this one. If you go back to the table, you will see alpha is very, very small. So if I square it, that's going to be even smaller. So if you don't believe me, let me stop sharing the screen and go back to this, where we were. These are the values of alpha. 10 to the negative 5, albeit this one is actually 10 to the negative 3 for glass. This one is 10 to the negative 4, 10 to the negative 5, 10 to the negative 5, 10 to the negative 5, and 10 to the negative... Sorry, this is 10 to the negative 7. What am I saying? And this is 10 to the negative 6. And all of these terms are 10 to the negative 5, meaning the biggest one is actually this one times 3 times 10 to the negative 5 for lead. So it's still, when you square it, it's going to be 10 to the negative 7. So instead of 0.00001, it's going to be 0.90 followed by 1. So when you square it, that's why what we're saying in here is just keep the linear terms in the expansion, and that's it. So when you square this, when you do the product in there, any term of the order of alpha squared is going to be ignored. And I will have an alpha times alpha, which is alpha squared, and this product of stuff. And I will have another alpha times alpha and this product of stuff. And I will have an alpha times alpha and the other product of the stuff. And then I will have an alpha cubed, actually. If that's alpha squared is too small, imagine alpha cubed. So it's going to be even smaller. So the biggest terms in here in the product for V plus V naught plus delta V, which is the new volume, by the way, when temperature changes, is going to be simply V naught plus alpha times, and I have the same value in here, V naught delta T, V naught delta T, V naught delta T, and that is 3 V naught delta T. So in a sense that after I cancel this one and that one, I will find that delta V should be 3 alpha times V naught delta T. By definition, this is beta times V naught delta T. And this is the proof that beta is 3 alpha. Okay. So this is, for this geometry, it's true also for this geometry too. For this geometry, all you have to do worry about in this case is R naught plus alpha times R naught times delta T. When you cube this number again, you do the expansion in here, you do whatever Taylor series and everything else, you'll find that the leading term in here is going to be R naught cubed plus this term in here, and again, because it will have an R naught times an R naught squared, and that too is an R naught cubed, times alpha, but you have 3 of them coming from this power, times R naught cubed, times, I'm sorry, because you take R naught out, so you're going to have basically at the end R naught delta T, okay? So it's going to be still linear, except that you have to take R naught out, and you will be left with 1 plus alpha delta T, so it's going to be 3 when you bring back the R naught cube. This is how it's going to look like. In any case, beta is 3 times alpha. So this is in a nutshell the proof for it. If you have any doubts or questions, please let me know. I think we did this in lecture. If not, this is basically catch up with that thing with the stuff from lecture. Does anybody remember? No? This is a question. Does this question make sense? Yes? No? Okay, very good. Thank you. You can leave the objective toward the end. You're going to come back to it if you want to. Okay. Basically, let's pull the activity in here on GeoGebra. And basically what it's saying is load the GeoGebra activity by clicking on the link above. Okay. You also have an Excel file that you will need to do the calculations, and I will tell you exactly what needs to be done on that Excel file. Okay. Here is the trick. You're going to record the values between 0 and 10 degrees, 2 values, hopefully one from the low end and one from the upper end. Okay. And collect 2 points of temperature and angles. So you need the temperature reading between 0 and 10 degrees, and also 2 of them, and also the angles corresponding to them. So you really have to be careful with this lab, okay? You have to really, because you will see the temperature as you turn on the furnace, the flames, the temperature starts to increase. So obviously, if you leave it for a long time under the flames, the temperature will increase. There is no limit to it theoretically, unless it goes through a phase transformation. So that's exactly what happened to your soup, for example, when you're cooking it. When you turn on the switch, when you turn on the heat, it's going to increase temperature. So that's exactly what's going on in here. But the point in here is, as the temperature rising, you're supposed to be paying attention to the angle also, because the material you sew it, and that's exactly the setup in the lab, by the way. If you walk tomorrow in the lab, this is exactly the setup. The material, as it's expanding, it's pushing on a rod, and that rod starts to bend. And as it bends, you're supposed to read the angle in there, okay? You're supposed to see how much the angle is changing, okay? Then repeat the steps. Do the same reading between 10 and 20, 20 and 30, 30 and 40, and 40 and 50. So at the end, you have a total of 10 points. Because between each range, there are 2 readings. So there is between 0 and 10, there are 2, plus 2, 4, plus 2, 6, plus 2, 8, plus 2, that's 10 points in here. And copy the data to the Excel file. Once you copy the data to Excel file, you need to complete this one. So basically, the Excel file should give you the R squared value, okay? Once that R squared value is given, and the alpha is given, you're going to also compute the error. The Excel should give you also the error based on the data that you have collected, namely the temperature and the angle in degrees, okay? Once you have that, you should be able to find what delta L over L naught is. because the Excel spreadsheet should give you that. Okay. Once that is given to you, then you're in good shape. Okay. Let me share with you the Excel spreadsheet so that we're actually clear onto what's going on. Hold on. Where is the stop sharing first? Stop share. And now share the Excel spreadsheet. So what the spreadsheet does is does some of the heavy lifting for you. You give it the temperature, you give it the angle, it's going to give you already delta L over L naught. Okay, it's this formula, basically. So if you really don't care about it, this is how the formula works in here. Can I change this value in here? Don't change it, okay? This is the formula that you will need for the calculations in here. I should really have locked this value, but it's fine. Now, it doesn't matter what you need to do. It's going to give you an R squared. How am I going to get my R squared? I have to go and look at the chart in here. The chart should give me the R squared. At this point, I don't have any data. So this is just a number in here. It could be any number. Right now, it's if I put 0, it's going to give me an error of 100%. If I put 10, an error is in negative 100%. So if I put 0.01, the error is 99%. So if I get 0.99, the error is 1%, okay? So at this point, when am I going to get the R squared? I'm going to get it from the chart. Once you go back into the data and fill out the temperature, the 10 points in here, okay? And give for each point the angle that you have carefully collected. Now, it's going to give you the alpha value, and it's going to fill out the delta L over L naught for you, all 10 of them. Then you're going to check the chart in here and read the number of R squared from it, bring that number and put it in here. So let's say, for example, it's 0.93. If it's 0.93, the error should be 7%. So at that point, I'm going to stop sharing the screen and I'm going to share with you the PDF file again. No, did I share with you the PDF file? No, I did not. Looks like I did not. Share. Where is the PDF file? Okay, so now imagine with me that you have filled the Excel spreadsheet. If you did fill the spreadsheet with this data that you have already collected from the GeoGebra activity, then you copy the data from the Excel spreadsheet in here for delta L, all of the corresponding values, and also the alpha that is coming from the Excel spreadsheet. If you have transposed correctly the value of R squared from your graph back to the Excel spreadsheet, which is this number, you're going to get an error percentage coming from the Excel spreadsheet you're going to report in here. So it all hinges on the following. You collecting the data and writing the value of R squared in here from the graph. Because this data in here is coming from Excel. This is coming from Excel. This one actually also coming from Excel, provided you have fed it with the correct value of R squared. Then you have the error. Then after that, it's just basically checking the error if it's above or below 5%. If it's above 5%, that there is something went wrong in either the simulation, which I don't think so, or you did not collect the data correctly, or somehow you did not transpose it correctly, or something like that. Typical errors, this one is the fact that you forgot to include the correct value of R squared in here. And then based on the value of alpha that you find in here, that's the last question, by the way. Based on that value, you're going to look into the table. Where is the table? I skipped it. Oh, it's in here. Where is the? Based on the value of alpha that you have looked in here, which material is closer to your basically have a mixture material in the GeoGebra activity. So in this case, which material is it? Aluminum? Is it steel? Is it, where is the value of alpha closer to? Or is it an alloy of some sort, combination of two or something like that? So that is basically a last question, and then you have the conclusion. So at that point, you know exactly what you're doing. So let me go to the GeoGebra activity, since we really have to rely on it. Where is it? Here. So here, I'm going to turn on the heat a little. So right now, as you can clearly notice, I have a reading in here, okay? Can I stop this one? No, I can't. So right now we are 10 degrees, we are 12. So at this point, I could record the value and move on. So you have to be very careful with your activity in here as you're doing this one, because as I was saying, it's moving super fast and you really have to catch it in those intermediate values, okay? So one technique that you can do in here, the heat now is so much temperature that the temperature has gone so high, okay? It's going to break the system, so it's not good to stuck it in there. So at any point in here, okay, did I say something wrong in here? Hold on. I may have gave you guys the, what is the instructions again? Not between 0 and 10. It's 0, 10. Yeah, that's correct. 0 and 10 degrees. Not 10 degrees Fahrenheit, 10 degrees angle. So the maximum you're going with this measurement is 50 degrees. Please don't get it to 50 degrees because it's stuck only because the device could not expand any further. So try to get it below 50 degrees in here. 50 degree angle, not 50 degree Fahrenheit or anything like that. Stop sharing in here. So it's still cooling down now. As you can clearly see, this is actually the setup in the lab, the physical lab. We have a rod in here that is fixed from this end, so it cannot move, basically. On this end, it can expand. In doing so, it's going to tilt this one a little. As it tilts, it's going to, the rod that is attached to it is going to bend a little. So it's going to push against it. So it has a little bit of leeway to move against it. And in doing so, we're going to measure this angle. And the formula that you saw in Excel actually has to do with this angle, this radius in here of this device, and the length in here, the arc displacement in here, and the angle measured actually in radians, not in degrees. These measurements of the angle are actually obviously in degrees. So the formula, if you look at it, has a conversion factor to convert from degrees back to radians, okay? This is exactly what you're supposed to do in the lab. In the physical lab, if we're there, you really have to take these measurements into account and do the conversions yourself and find the actual length, how much this one has extended in length on this side, do the temperature that has been turned on in the bottom. So now it's on. Now you can clearly see I have already probably, you have to pay attention to the graduations. You have 1, 2, 3, 4, and 5. So each 2 points are actually 2 degrees. So right now it's 20, 22, then 26. So one way of doing this is to actually watch numbers for yourself. Okay, see the 2, which usually has a lot of errors with it. And as you move along, watch the 8. Once it reaches the 8, read the temperature. Watch, for example, the 12 and read the temperature. Watch the 18 and read the temperature, and so on and so forth. And now you have a good, nice set of data. If you think the data is not good enough, you have to repeat this experiment time and time again to train yourself on how to read this one. Once you have it, then you have good enough measurements to report on the table and send it to Excel. As I said before, this is a very fast lab, but I'm expecting you guys to finish it quickly and do the report, and that's it. Any questions? Oh man, forgot to watch this laptop finish its task. It's turned off because it's not plugged in. Any questions, guys? No? Okay. So here is the deal, as before, okay, since this is a lab, I'm going to leave the microphone on, the speaker on. I'm going to turn off my microphone. I'm going to turn off the video. I mean, my video camera. I'm going to stop recording. If you guys have any questions, you can speak up and give me about no more than half a minute to run back to here and answer your question, okay? If you choose to finish this lab later, that is fine too. You still have the option, if you have questions, to send it to me to finish. It's not due today, so you have plenty of time to finish it. So if you cannot finish it today, that's fine. I think you have, like, what, almost 10 days to finish this lab reports. So if you choose to leave now, that's fine. If you want to hang around until the session is over, that is fine too, okay? Good? Okay, very good. So I'm going to stop the recording now.